Hey, what's going on? So I was driving home from some bar trivia. We got third place, 9 out of 10 in the sci-fi category. Who's ever heard of Avenue 5? Anyway, when I was driving home and I was listening to a podcast and I heard this clip.
I've always wanted to figure out the math on the minigun rocket jump. The backward recoil of a minigun, is that enough to lift a small person?
And immediately I thought to myself,
I can do that. I can do that. Take the gun.
Well, let's find out. Is it possible to use a minigun as a jetpack? So important things we're going to need to know before we get started. We're going to use the M134 as the minigun. I assume that's what he's talking about. It's what comes up when you Google minigun. We're also going to need to know some important facts about that M134. So to start, the weight of the M134, I'm going to say weight, G for weight gun, is 85 pounds. It also has a rate of fire of 6,000 rounds per minute. Maximum. And the round it shoots is a 7.62 by 5.1 NATO round. Now, when you Google that, the Wikipedia gives you three options. There's a 140 grain, a 150.5 grain, and a 174 grain. The 174 is long range, so that's not what we're looking at, I think. And I already did all the math ahead of time. Spoiler alert, and we want to go with the 150.5. It gives us our best option. So the 150.5 grain round has a mass of around 9.72 grams and a muzzle velocity of around 856 meters per second. So the first thing we're going to need to do is find out how much force the minigun puts out. And to do that, that's pretty easy. We just use a Newtonian equation. F average equals delta P is our momentum for this over delta T. Our change in our momentum over our change in time equals our average force at the end of the gun. Momentum is defined as M times V. Now the change in momentum is going to be from the starting point to the point it leaves the barrel of the gun. Because once it leaves the barrel of the gun, it's no longer acting on the gun. Now we've finished our interaction with those two bodies. So the change in momentum for our bullet is going to be equal to the mass of our bullet times the V at the muzzle minus the mass of our bullet times the V at our starting state. The bullet's in the chamber, it doesn't have a starting velocity. So that means our initial state is 0, which means that our change in momentum is just our mass times our muzzle velocity. So our change in our momentum is equal to the mass of our bullet in kilograms times our muzzle velocity, which gives us a value of 8.32 kilogram meters per second. Now our delta T is the time between each round, which is going to be 1 over the frequency of our rounds, or our rate of fire. Now our rate of fire is in rounds per minute, so we want to turn that into rounds per second, which for 6,000 rounds per minute, it's just 6,000 over 60, right? 60 seconds in a minute. We end up with 100 rounds per second. So our delta T is equal to 1 over 100, which when we divide our momentum of P by 1 over 100, it's the same as multiplying it by 100. So our average force is equal to 8.32 kilogram meters per second times 100 per second, which gives us 832 newtons. So to convert that into a number that makes sense for whoever's probably watching this video, 832 newtons is equal to about 187 pounds. So just from the start, we can see that our average force from our gun is 187 pounds, but the gun itself weighs 85 pounds, which means the largest person we could launch without even accounting for the mass of our ammunition is 102 pounds. And we're against child soldiers, so we're not going to do that. And last I checked, Ariana Grande is in the listing, so that's not going to work for us. So what are we going to do about it? I give you the M268 lead-propelled Death from Above jump pack. Jetpack Kermit edition. Let's box this off for stage 1 so we don't have any confusion. So now, the weight of our gun goes up from 85, now we have 2 of them. Weight of gun goes to 170. But our average force from 2 guns also goes up, and our force becomes... Where did I draw that? 374 pounds of lift, or thrust. So now we have an available 204 pounds. That's a lot more. But obviously we aren't going to throw a 204 pound man on there. No, we need space for our ammunition and various other things that are needed to operate the gun. So let's say instead our person weighs, I don't know, 155 pounds and is about 5'8". Now we're also going to need to account for the mass of our ammunition and a couple other things. So we'll say each bullet is represented by WRD, weight per round, and that weighs 25.4 grams or 0.896 ounces. Now we're also going to need to chain all of this ammunition together, and the standard appears to be an M13 link. The M13 link, we'll say WL, weighs 4.35 grams or 0.153 ounces. So for every round of ammunition we're carrying, we're going to need to add these two together. So we'll say, I really wish I hadn't used WRD already. We'll go with WB, weight bullet. That's not great, but it'll have to do. The weight of a bullet is 29.75 grams or 1.05 ounces. Now we have our ammunition, we need to figure out how we're actually going to launch this. Either we're carrying it all with us on our back like a fuel tank, or it's going to just hang down to the ground and just feed up to the guns from the ground, and we pretend we have an unlimited supply. This is going to give us two different answers. With the one that's feeding up from the ground, we can find what our sustainable height would be, how high we would actually be able to just sit at equilibrium. With the fuel tank option, we would be looking to see how high we could jump with just one burst of ammunition. So let's do both. First, we're going to see the continuous feed one, the one that gives us our equilibrium. It's easier math to do, so we're going to start there. So in order to know that, we're going to need to know the distance between each round, which the M13 link has a distance of about 0.58 inches. So DL for link is equal to 0.58 inches. Now, if you're 5'8", according to the internet, I found one answer and that was good enough for me. According to the internet, your shoulder height is 56 inches. So if we assume that our ammunition is feeding in at shoulder height, we can say that the amount of ammunition we need to have from a standing position is going to be 56 inches divided by 0.5 inches, which gives us number of bullets standing is equal to 97. 56 divided by 0.58, roughly. Now the other thing we're going to want to account for is the ammunition isn't going to be able to feed up like this and then immediately turn sideways into the gun. It's not a P90. So we're going to just assume that we're just going to add an extra like 20 rounds that is going to be taken up in creating that curve that's going to be necessary. That's probably close enough. So now instead of having 97 bullets, we have 117 bullets. But that's only bullets per gun. Remember, we have two guns, so we need twice the amount of bullets. We're going to say NBT for true, our true bullet count that we're using for standing, is actually going to be 234 rounds. So now we can multiply it by the weight of our bullets to get the weight of the ammunition we have to carry just from starting standing. Gonna give us WBS is equal to 234 times 1.05 divided by 16, because it's 16 ounces per pound, gives us a weight of 15.36 pounds. So that's just the mass of our bullets that we have hanging. Now, another thing to note is that the M134 requires a power supply that has to be able to provide 24 volts at 58 amps, which means we have to use a pretty specific, in fact, it should be a 2-conductor, 0-gauge aluminum wire. That's like the minimum for a guesstimate of, we're going to say, maybe 30 feet. So the linear density of 2 aluminum gauge wire is given to be 0.16 pounds per foot, or 0.0133 pounds per inch. So our weight cable standing is equal to 56 inches, right, times our density, but we have two cables for two different guns, so times 2, which gives us a weight of around 1.5 pounds standing. So our total standing weight, which we'll say is WTS, can be written as WG, weight of our gun, plus WP, weight of our person, plus WBS, weight of our standing ammunition, plus WCS, weight of our standing cable, which works out to 341.86 pounds. So even with our guns, our person, our bullets, and our cable for our power supply, we still have a lower weight than our upward force. That's good. That means we're actually going to start accelerating upwards. Now, to find out how high we can actually go, we just start adding weight until we reach the point where our weight matches our upward force. Once our weight pushing down equals our force pushing up, we've reached a net zero force. And that will be our equilibrium height, how high we can fly, assuming that we're able to just keep constantly running these guns at 6,000 rounds per minute for an indefinite amount of time. I'm not actually sure how long it'll take us to get there. So the way we do that is we find out what our net force is, F net, which is going to be equal to our F average minus our weight total standing, which gives us a net force of 32.14 pounds, pushing up. So now what we want to find out is where we've added enough ammunition and cable to weigh as much as our F net. So we just set F net equal to the weight of our bullets in pounds divided by the distance between each link, so 0.58 inches, plus the linear density of our cable, so that 0.0133 pounds per inch, multiplied by our height that we want to solve for. Height, we'll say HE, height of our equilibrium. So now we just divide F net by whatever this adds up to, and it should give us HE, which gives us a number of HE equals 258.3 inches, or right about 21.5 feet. That's a pretty good jump. Now, the question he had was specifically, I think he asked was, can you launch someone? Now, what we can do is we can take our initial starting point and we can just use our standard F equals MA. And we know our upward force is 32.14 pounds and our mass is whatever the kilogram equivalent of 341.86 pounds is. We can find our acceleration, which I will spare you the details, but the acceleration ends up equaling 0.92 meters per second squared, or in something you'd be probably more familiar with, about 0.09 G, which I wouldn't really say that's launching something. That's really more of a suggestion that you move upwards, but I guess at a greater rate than the Earth is suggesting that you move downwards. Now, real quick, I also did this math again for the Dillon Arrow lightweight version, which has a weight per gun of 43.5 pounds, but it can only sustain a fire rate of 4,000 rounds per minute, which, if we do all that math out again, gives us a weight total standing of 258.86 pounds. But because of that lower rate of fire, our F average is only 249.4 pounds, which is lower than our weight total standing, which means that this doesn't work. We can see that that high rate of fire is really important. If there is a lightweight version that can sustain that 6,000 rounds per minute, and I'm just not familiar with it, I did the math just in case, that would have a maximum height of 77 feet and an upwards acceleration initially of 0.44 Gs, which the Saturn V did 0.3 to 0.4. So I guess that would actually count as a launch. But we'll stick with this. Our equilibrium is 21.5 feet. That's pretty good. Now, what if instead we were going to use it like a fuel tank and we just had a burst? This was going to take some actual rocket science, so booze break. They say you shouldn't drink and derive. I don't give a flip! Alright, back to the show. So if we want to treat our ammunition as a fuel tank, we need to know how much we can carry to actually launch our jetpack. And that's actually pretty easy to figure out. All we have to do is take our net force and then divide that by the weight of our bullets. I'm going to put this in pounds. It's going to be easier if I just remember. Yeah, divide our net force by the weight of our bullet, which gives us our number of bullets is equal to 32.14 over 0.0656, which equals to about 490 rounds. Now, let's not forget that we have to split that 490 rounds between the two guns. So instead, each gun gets 490 over 2, gets 490 over 2, which gives us 245 rounds per gun. But wait, there's more, because remember, we accounted for all the ammunition that was required just to reach the ground in our initial force calculations for our FNet. So all that ammunition that was accounted for is also going to get to be fed through our gun. So in fact, the number of bullets total for our gun is going to be 245 plus that 117. Yeah, plus that 117 that we had before, which gives us a total of 362 rounds. Now, we know that our gun fires at 100 rounds a second. We already did that. So if we have 362 rounds for each gun, we know that we get 3.62 seconds of thrust. So how do we take 3.62 seconds and find out how high our rocket goes? This is where rocket science comes in. There's something called the Tsiolkovsky Equation. Spelled, I'm pretty sure, like that. Tsiolkovsky, Tsiolkovsky. And Tsiolkovsky's equation says that delta V, the change in speed of your rocket, is equal to the speed of your exhaust times the natural log of your mass initial M0 over your mass at point 1. Point 1 being wherever you're taking your time to be. For us, we're going to use 3.62 seconds, our time at burnout. Now, we don't really have a good VE because instead of using like a steady stream of gas, we have bullets that we're launching out at a rapid succession. So in that case, the VE is accurately described as our specific impulse. Specific impulse can be accurately described as the thrust per mass flow. Now, we have a thrust, which is our force average. And we have a mass flow because we know how much each bullet weighs and how quickly they're being ejected. So specific impulse is equal to our force average over the change in the mass over the change in time, which we can rearrange to be the force average times the change in time over the change in mass. Plugging this back into our Tsiolkovsky's equation, we get that the change in velocity at burnout, when we run out of fuel, when we've expended all of our 362 rounds, is going to be equal to the force average times the change in time, which we're going to take to be our 3.62 seconds, divided by the change in mass, which is all of our bullets. We've expelled all of our bullets, so however much that weigh, that's our change in mass, times the natural log of our initial mass, which is going to be that 374 pounds, right? Because we've packed up as much mass as we can, equal to 374, and once we start wasting bullets, we'll start losing mass, and then we'll be able to launch, right? So our M0 is 374 pounds, or the metric equivalent of that, and then our M1 is going to be that 374 pounds minus the weight of all of our bullets that we're expelling. So if we take this up here, for this to work, it's a lot easier to convert it into metric. So I'm going to do that because I don't want to figure out how to do mass in imperial. We're going to take it up here for clarity. The delta V is also just going to be our velocity at burnout because we have an initial velocity of 0. So VBO is equal to, this force is 832 times 2 because 2 guns, again, 1664 newtons times our time of 3.62 seconds divided by the mass of all of our bullets, which when we convert it to metric is 21.54 kilograms, times the natural log of our mass ratio of 169.64 kilograms over 148.1. Now that's if we're just in space. This doesn't account for the fact that we also have gravity. In order to account for our gravity, we have a minus the... In order to account for our gravity, we have a minus the acceleration due to gravity times our time, which is 3.62. The acceleration due to gravity will be 9.81. Solve all this out, we get VBO is equal to 2.46 meters per second, which is to say when we've expelled all of our bullets, we have an upward velocity of 2.46 meters per second, which is about 5 miles per hour. So that's pretty neat. We'll know how fast we're going, but now how do we know where we are? To find that, we go back to our Tsiolkovsky equation, because we can actually reclassify our Tsiolkovsky equation to, instead of being at the maximum point, we can turn it into a equation that defines our velocity as a function of time. And the way we do that is we take delta V is equal to our force average, because that's going to be continuous, times our time divided by our change in mass is going to be our mass flow rate times time. Our mass flow rate is going to be that weight of our bullets times 100 per second, right? Because we fire 100 bullets per second. Times the natural log of still that initial mass M0 over M0 minus M dot T, the M dot being our mass flow rate once again, because at any point T, that gives us our final mass or our mass at that point, right? Minus G times T. That gives us a velocity. Since we're starting from 0, the delta V is also our velocity at that time. So that gives us a full description of our velocity as a function of time. Now, velocity can also be said to be the derivative of the position. So h of t, height, is equal to the integral of v of t with respect to time. If we integrate this from 0 to 3.62, that will give us our height at 3.62 seconds. And I could probably spend a few hours figuring that out and deriving it on the board, but I'm not a sophomore in college, so I'm gonna do what every adult engineer does, and I'm gonna put into Wolfram Alpha and let the Copperbloods do it for me, which I did ahead of time. So I'm just gonna use my notes and put it on the board, and you can see I'm not lying if you want to zoom in and get the exact numbers and check these yourself. But it's really long, and I don't expect you to read it, but that's it. And if you're like, well, what about plus c? Well, nerd, we know that h at time 0 is equal to 0, and if you plug 0 into this t, then we know that's going to become 0, and 0 into this t, that becomes negative 28.5109 over negative 28.5109. The natural log of 1 is equal to 0, so that also becomes 0, which means that we don't have a constant. Okay, so now it's really simple. We just say that our height at burnout is equal to our height at 3.62 seconds, which is equal to 2.9 meters. Now that's just our height at burnout once we've run out of ammunition. But remember, we still have a velocity, an upwards velocity of 2.46 meters per second. So we're still going to be carried up a little bit more. So what's our actual max height? To find that, we're going to do a balance of energy. So for any system, the total energy can be defined as the kinetic energy plus the potential energy plus like thermal energy and blah blah blah, but those don't actually apply to us right now, so that's going to go to 0. We don't care about that. What we care about is our kinetic and potential energy. Kinetic energy is defined as 1/2 mass times velocity squared. Potential energy is defined as mass times gravity times height. So the mass of our object in both cases times the gravitational constant, that 9.81 seconds, plus the height it is off the ground. So we want to find what our height is at max. We know our height at burnout and our velocity at burnout, so we can define our energy at burnout as being the mass times gravity times h burnout plus 1/2 mass times our velocity at burnout squared, right? Now, in order to find our final height, when you hit the top of your arc, once you've reached your peak, you no longer have any more velocity. Now you start accelerating back downward. Just for that minute instant, your velocity is 0. so our kinetic energy would be 0. In that case, the energy, okay, this is annoying and in my way, so I'm gonna get rid of it. Okay, in that case, the energy at zenith, our peak, is going to be mass times gravity times our height at burnout plus the height difference, the delta H. And we're trying to find that delta H. Well, because of conservation of energy, energy at burnout equals energy at zenith. So we can say mg times HBO plus delta H is equal to mg times HBO plus 1/2 mvbo squared. I don't know if this is even readable at this point. Whatever. I hope you're following along. I don't know. I'll get down here and try and write better and bigger. So if we multiply out our HBO and delta H, now our energy at zenith becomes mg times HBO plus mg times delta H, which is equal to mg HBO plus 1/2 mvbo squared. Now, these are on both sides, so we can cancel those out. We can subtract that from both sides, right? So we're left with mg delta H is equal to 1/2 mvbo squared. And then m cancels out, goes to 0, which gives us that our delta H is equal to vbo squared over 2g. If we punch that into a calculator, we get that delta H is equal to 0.308 meters. Now, our total height is going to be H burnout plus our delta H, which when we add them together, gives us HZ is equal to 3.21 meters, which is equal to right about 10.5 feet. Which is honestly a lot higher than I expected. Now, if we put both cases together, where say we get to our equilibrium, and then once we're at equilibrium, we cut the chains, now we're gonna start losing weight again, which means we're gonna be able to actually force ourselves back up more, and we're gonna go up that extra 10.5 feet. So 21.5 plus 10.5, 33 feet, 32 feet. You should trust my calculus because I can't do arithmetic. So to answer the question, can you launch someone with an M134 minigun? Well, not one, but assuming you have enough money and time and someone with the adequate lack of self-preservation instincts, yeah, you can get them like 30 feet in the air. Anyway, this is a little different than the videos I usually do. The Northrop flying wing video is still coming, but I thought it'd be fun to break out some math I haven't done in a long time. If this is the kind of thing you want to see, you can comment that or like and subscribe to the video. I'll know that that's something you enjoyed. If you're new to the channel, I don't usually do a lot of math. I usually just talk about the history of like an engineering design, and then usually I talk about some concepts like on a broader scale. I don't usually break them down into math. If that sounds interesting to you, check out the channel. So anyway, thanks for watching.
He never did land a ticket that day. Yes, sir, no matter how hard he tried, he couldn't change the fact that he was indeed old and fat.